And sorry, everybody. My name is Jeremy Agor. I'm the Director of Communications and Marketing here for the College of Engineering. Welcome to today's virtual brown bag session with Dr. Weidong Zhou from the Electrical Engineering Department. A couple housekeeping items to start. First of all, we do these virtual brown bag events every day, and the full schedule you can find on our College of Engineering website. Also, the link to the full schedule is in the Q&A box on your right-hand side of your screen. As we go along, we will be taking questions. If you type your questions into the Q&A, we will monitor that and we'll ask questions at the end or as necessary during the presentation, most likely at the end. Without further ado, I would like to introduce Dr. Zhou. Dr. Weidong Zhou is a professor of electrical engineering and a distinguished university professor at UTA. He directs a group working on semiconductor devices with a focus on optoelectronics and lasers for silicon photonics. He has authored or co-authored over 350 journal publications and conference presentations, including over 120 invited conference and seminar talks. His research has profound impact in the field with publications in very high impact journals such as Nature Photonics, Nature Communications, Nature Biomedical Engineering, Science Advances, and others. His work is also of great commercial potential with applications in smart society, smart manufacturing, smart health, and sustainability. He is a recipient of the College of Engineering Excellence in Research Award, the University Award for Outstanding Research Achievement or Creative Accomplishment, and he was inducted into UTA's Academy of Distinguished Scholars in 2016. In 2014, he was elevated to Fellow of SPI, the International Society for Photonics and Optics. Recently, he was elevated to Fellow of OSA, the Optical Society, for significant contributions to photonic crystal membrane lasers and hybrid nanomembrane optoelectronics. So, Dr. Zhou, I'll hand it over to you, and we look forward to your talk.
Thank you, Jeremy, for the wonderful introduction. Well, good morning, good afternoon, everybody. This is my great honor to present today as part of the College of Engineering Brown Bag series. So I'm Weidong Zhou from Electrical Engineering here at the UTA. So I was told this talk is like a more basic, TED Talk kind of introduction about my research. So I put a title, try to be a little bit more general. So the title of my talk here is I call Light is the Future of Electronics, okay? Specifically, my research work on photonics, essentially, or dealing with light, essentially. And my focus talk today will be looking one of the areas of focus in my group, which is the kind of semiconductor laser research with the potential applications for sustainable smart society. Of course, before I get started, I will acknowledge, of course, all my current and former group members, as well as collaborators and funding agencies. So as we know, we are in a connected world or virtual world or smart society, whatever you call, or digital society. Bottom line here is we are relying more and more on the virtual connectivity or online presence. As you can see here, we talk about the Internet of Things, 5G, artificial intelligence, or dealing with the big data, everything based upon kind of connectivity among ourselves. And this pandemic also makes this even more desirable. So in terms of the backbone to support such kind of connectivity, the very first part is really this so-called fiber optical networks, where we were able to transmit data at much higher capacity at much higher speed. In addition, we will deal with so-called cloud or data centers, where have a humongous data need to be stored, processed at many kind of mega data centers by Google, Facebook, Amazon, you name it, so across the world. Of course, in addition, we have all these devices surrounding us, so-called Internet of Things, where you have so many different kind of smart devices connected on a website. In fact, people predict by 2025, 2030, in average, in the world, we have average about somewhere 6 to 9 connected devices per person. Okay, so think about 7 billion times 5 or 7, right? That's about 60 or 70 billion devices connected to a network. Okay, and if you look locally, right, one of the things we're looking, of course, smartphone. Let's say this shows kind of iPhone 10 here. It has lots of optical components inside, whether for your Face ID, for projector later on, for of course for camera, for even for those kind of flashlight. And if you notice, there are multiple different kind of laser devices inside your iPhone already. And of course, another very emerging and potentially very disruptive area is the light applications, where we have this UAVs and unmanned and automatic and autonomous car system, where heavily rely on laser-based ranging system. Okay, so in summary, I would argue photonic technology is a backbone of this smart connected society. And specifically, I would argue, all around those areas, laser is one of the key devices driving behind those networks for data flow. And this year, in fact, is a 60-year anniversary of the first laser invention. So this kind of one of the special issue from optics and photonics news by Optical Society. So we can argue laser is everywhere, it's ubiquitous, right? So I call it the engine of the data infrastructure. So what's a laser, right? So laser stands for light amplification by stimulating emission of radiation. So basically, you have an emission media, for example, we call it game media. Basically, you have a light generation or light emission material media. In addition, you have a feedback mechanism. In this case, could be 2 parallel mirrors or reflectors. So light being kind of bouncing back and forth in a cavity formed by this 2 parallel mirror to create kind of amplification. And as a result, you may reach in so-called stimulated emission, where you have a lazy generation, where the light is very different from a conventional beam, like a LED. I will show briefly. So typically, you have 2 kind of laser cavity traditionally being used already in the data centers or commercial devices. One is on the left here shows this we call edge emitting laser, where the facet is formed by cleaving 2 semiconductor surface along the crystalline. So you have these 2 parallel mirrors formed as a cavity. Then light coming from the edge of the facet or the wafer, we call it edge emitting laser. Another kind is called vertical cavity surface emitting laser, where laser is coming from the surface normal direction. You can see here, the cavity is formed by 2 multi-layer stacking reflectors formed by essentially we call it bracket reflectors or distributed bracket reflectors to have a high reflectivity. The basic principle is also a FB cavity, except it's kind of along a vertical direction. As I mentioned, this laser is very different, whether it's edge emitting laser or VCSEL, from the conventional so-called light emitting diode. Typically have this very broad, large beam divergence angle and very kind of wide spectral range. So laser is coherent. It's very kind of beam is really collimated. You can see here, and between VCSEL and edge emitter, there's some small difference. But generally speaking, laser is much better in terms of higher beam intensity, also higher speed for data network. Okay. As I mentioned, a laser was invented about 60 years ago from first ruby laser, 1959, and then 62, this first diode laser formed. So as I mentioned, based on the application we have so far, semiconductor lasers are one of the greatest inventions in the 20th century. It's a basic building, forms the basic building blocks for electronics, for internet, and a smart society, or in general, data infrastructure. Just give you one example, the VCSEL devices I mentioned earlier already see a huge market in penetration. In 2017, the market share is about 330 million. Now people predicting by 2023, a few years, you're reaching 3.3 million. 3.5 actually trillion actually, with 3.3 not trillion, billion, sorry, with 3.3 billion chips formed. So what's the problem then? Laser has been kind of widely used, right? So there are two issues I highlighted here. One is we mentioned these devices we call the silicon electronic scaling, where we see all this very compact, powerful cell phones or computers, and it's all based upon this so-called Moore's law, where the scaling of silicon integrated circuits was kind of very successful for the last 50 plus years, where you see billions of transistors on a single chip. Okay, so if you look at this wafer here, you have multiple die chips. Each chip have billions of transistors processed. Accordingly, you have to connect all these devices. You have this called electrical interconnect. Typically, it's kind of metal wires, gold or copper, different kind of metallic materials. Because this large amount of transistors on the chip, you also require a large amount of electrical interconnects. You can see it's tens of kilometers already in the tiny devices here. So it's very, very challenging. Very, also you can see later it's a big issue. Finally, so we call this processing in the kind of node dimension here, from initially tens of micron in the beginning of the 1970s, now to a few nanometers. Approach the limit. Okay, so because of the advance of the semiconductor and the manufacturing process, we see a huge penetration, a huge advance in the electronic devices. Okay, so we can also say that the invention of transistor in 1947 and also integrated circuits by actually Jacobi in Texas Instruments in 1958 is indeed another great invention in the 20th century for data infrastructure. But the challenge that I highlighted here is we are reaching a limit. We're reaching a limit in terms, power density and efficiency. That means you're packing more and more devices together. So it's a major challenge in further scaling. Also, speed is limited. Power consumption becomes a major issue. And another problem is the time delay also, because of the tens of kilometer electrical wire here is a problem. So that's a big problem. The second problem is connectivity. I mentioned that data center, you have a huge amount of data there. To connect the data, and to be able to move around the data across different racks here, you need a large amount of connectivity, and those now is done by fibers as well. And because the increase or expand increase of this demand for data traffic, you see a 73% per year kind of data center traffic. This means you need a large capacity of fibers to be able to support this kind of demand. And we know fiber or optics in general is much faster, has the highest bandwidth capacity compared to electronics. As you can see, show this chart here, that's typically 100 gigabit per second each bandwidth for electronic lens. But now for optics, you can reach 25,600 gigabit per second. So you can do 3-order improvement compared to electronics. However, currently what we are doing now is fibers. So you can see a huge amount of connectors and the fibers. So if you look at the back of the data center, you have a large amount of the fibers trying to connect individual racks. So that's become another bottleneck in terms of how to further improve the capacity. And energy efficiency, that's of course another issue here to be addressed, how to make it efficient. So those two major issues are facing our community, and that's where we are working on as well. So one solution, we and many groups in the world, in fact, is on this so-called silicon photonics. So the idea here is we know we can do very well on silicon for IC fabrication. It can be very low cost, high volume, and highly integrated. It can be scalable. Integrate with the optical technology, we already be successful in the fiber optical communication networks, where you use discrete laser devices or detectors and fiber networks with extremely high bandwidth, long distance, and also immunity to electronic noise. If you combine these two, then you create a scenario where you can put the optics alongside with the electronics on a silicon wafer to have a combined benefit of high volume, low cost, as well as high bandwidth and long distance. So it becomes called optics anywhere. Okay, lots of potentials. So, and we can see essentially silicon photonics can be mentioned as a combination of two of the most important inventions of the 20th century I mentioned earlier. One is the silicon integrated electronic circuits. Another one is semiconductor lasers photonics. Indeed, over the last 20 years ago, you see a tremendous progress has been made. In fact, I would not call it a potential now. It's actually have lots of real applications in the field. You can see on the left side, it shows kind of different applications from data center to quantum computing to high performance computer and to also consumer electronics, sensors, aerospace, etc. On the right side, it just shows an example of many different photonic devices made on the silicon-based material system, where you can be different kind of, real different functionalities from RF to, bio, to, of course, optical switching and microwave photonics and etc. Okay, so it's tremendous progress already, but there are issues here. I say silicon is a good material. What's the problem here? Is we need a laser. Laser on silicon indeed is a very challenging issue. Silicon, unfortunately, is not a very efficient light emitter. So this just give a quick, kind of snapshot about why. Okay, so this is a typical we see as a band diagram shows in for a semiconductor. We call it energy momentum diagram. Shows this in the conduction band, valence band for semiconductor, where if you have a conducting band minimal and valence band maximum aligns along a K space or momentum space, we call this kind of called direct band material, such as gallium arsenide in phosphide. We call it group 3, group 5 material in the periodic table. So those are direct band materials. They're very efficient for light emission. That's what we made all the lasers based on those compound materials. On the other hand, the silicon is an indirect band material because the minimum of the conduction band, maximum of the valence band are not located on the same position, the K space. So it's inefficient for light emission. In fact, it's very hard to make a light emitter out of it. And of course, we know if you have a complete optical network on the chip, you need different components. Laser is one of the key elements, of course, in digital modulators, to fibers, electronics, etc. Okay, to waveguides. So laser remains to be one of the major challenge. And the challenge I summarized here, there are threefold. One is, what kind of cavity can form on the silicon, what kind of material you can integrate on silicon, and ultimately also you have to worry about energy efficiency as well. Indeed, silicon, among many other groups, has been very successful in address this issue over the last 20 years of research and a major effort push on this. They have been trying to integrate a kind of so-called edge-emitting laser on silicon using a process called a wafer bonding process. The idea is basically to put a 3-5 laser material on top of silicon, use silicon as a waveguide. You can see here, you have this 3-5 game material on top, and they have a silicon waveguide as a laser cavity. So automatically you can form this edge-emitting laser on a silicon wafer. So it has been very successful and addressed many issues in terms of reliability and the process. And they also was able to successfully integrate into their transceivers for data center, and also be able to use this kind of humongous capacity, switching capacity, Ethernet switch with the silicon photonics and the hybrid laser inside here. They have be able to integrate. So it has been very, very successful already. However, there are different issues as well, we argue. One is the wafer bonding process is not necessarily the best approach for integration here, because you have to do wafer bonding and then you have to remove the substrate. So that process, I think, is not ideal. Secondly, we will see later on, the energy efficiency could be an issue because the intrinsic cavity size is very large. So what we have been working on also for almost 15 plus years now, since I joined the UTA in 2014, is called transfer printed photonic crystal lasers. Okay, so what's the photonic crystal? So okay, that's the one slide from Scientific American in 2001, where Eli Yablonowicz is one of the pioneers, proposed this photonic crystal cavity. Essentially, the idea here is they call it nanostructured materials containing ordered arrays of holes could lead to an optoelectronics innovation, doing for light what silicon did for electronics. So the idea here is basically have this kind of periodic structure drill into the dielectric material to manipulate the photons. And luckily, when I was a student at Michigan, we are working on this kind of very exciting front-edge research area also early on, where we were one of the first groups demonstrated the electro-pumped photonic crystal defect mode laser on the gallium arsenide material, the compound semiconductor material. So that was kind of one of the major breakthroughs then. So after my graduation, I went to a company for a few years. Then when I joined the UTA, I would think about my research. Then of course, photonic crystal naturally come into my mind. But then my key purpose changed, because after witnessing this telecom market crash in early 2000s, we found out optics is extremely powerful in terms provide huge capacity of bandwidth. On the other hand, we need to look into something also be able to scalable for massive and low cost market, and also to address the issues on the silicon integration aspect. So that's what we looked into silicon photonic crystal structure to address the issue of lasers on silicon. So the idea here is instead of looking into a defect mode laser where you have a periodic structure, you have a removed one in the holes to have a defect cavity. That's what we used as a band gap material. We look into, can we have a reflector made in a perfect two-dimensional periodic structure where you have 100% reflection to form a mirror based on this single layer structure. And indeed it works. In fact, later on you can see people talk about this now is in fact butterfly wings with kind of shiny color. If you look into kind of SM image, you have this kind of skeleton where you have a periodic structures with a dimension in the order of hundreds of nanometer, matches with visible wavelengths. That's why it's a different color reflection come out of this butterfly wings. So you already see some kind of, it's called wavelength selective reflectors from butterfly wings. And that's what we have been working on for many years now, is drilling the holes on the silicon, thin film silicon. You can see that's use the E-beam, electron beam lithography process for nanofabrication. And this hole size is about 100 to 500 nanometer size with a periodicity about 1 micron. And we can make it, of course, a large area. And if you design it right, indeed, you can get 100% reflection or 100% transmission, depending on different wavelengths. So you can design that. So, and of course, the initial theory was inspired from Professor Xianghui Fei, which is my collaborator, because we're friends now, and from Stanford. And also, in fact, Professor Mechanism is one of the pioneers of multi-gradient-based guide mode resonance gradient structures, which can be reached similar functions. And later on, you have high conjecture index grading as well from UC Berkeley, Professor Connie Chang, Hasanai group. And now recently we have many other people talk about dielectric meta-surface-based reflectors. So bottom line here, there are many different kind of periodic structures you can use to realize this kind of functionalities. And we have been working on this since 2008. You can just a kind of quick snapshot of what has been achieved so far, where we see kind of filters, reflectors, detectors, and then of course different kind of structures, and then finally reflectors. You can see we can make a 100% reflection on the silicon, and also later you can see on the glass platform. So that's very good. So then to form a laser, we need a gain medium. So our idea is to form kind of mixed kind of structure. We have a 2 single layer reflector with a gain media in between. That's the structure we have here, to replace a 2 thick DBR with a single layer reflector and use a 3.5 gain media in between. Then the next question becomes how to put this gain media inside here. Okay, so this of course we have many advantages here in the photonic crystal reflector as a cavity. I talk about this microtransfer printing shortly for heterogeneous integration, and then of course wavelength scalable, and it's a silicon CMOS compatible. So how to integrate different material together? So that's another innovation we call the micro transfer printing here, where we put a 3-5 material and silicon together. The idea is very simple. We typically only need a top thin layer of thin film of functional layer here to realize the functionality. The rest of the substrate we have is used as a mechanical support. So what do we do here? We just simply release some functional layer from a substrate so that we can put the functional layer onto another material. Okay. For example, we pick up this thin layer of silicon, use a PDMS in the polymer stem, and print onto a different substrate here. By doing so, you can have a 3-5 integration, thin film onto silicon, or you can even make this kind of flexible crystal silicon. I don't have time to talk about it. That's another very interesting area of research. So with this in mind, now you can put many different materials together now. It's just a peel off different pieces of functional layer, put onto the same silicon or any substrate. Okay, so multi-material integration. For example, I mentioned here already, just to quickly show you how it works. And then you can do a multi-layer stacking, layer by layer, put a different layer on top of each other. And then finally, you can put on a flexible substrate as well, or glass or polymer. So very powerful. Here, just show some like book chapters. We contributed to this too in the books. Talk about this membrane process for integration, either for silicon-based electronics or photonics, or for flexible optoelectronics. That's what I achieved. So realize the laser on this silicon substrate with silicon photonic crystal reflector and a transfer printing process. In fact, the review called rubber stamp for silicon photonics. Basically, you pick up the material, use PDMS, and print onto a different material. And then now this field pick up quite a lot in Europe, in Asia, and in the US as well. So what do we work on now? So we work on now the third challenge I mentioned, energy efficiency. Okay, so in other words, how to get the laser cavities further scaled to get the device more efficient to carry the data. Here shows kind of a generic network optical link, where to travel a signal through the fiber, you need a transmitter, which you have a laser there with the electronics to convert electrical signal into optical signal, and then your optical signal will be referred back with a receiver detector there. So of course, you need a laser transmitter to be efficient. What one figure merit we call is energy cost. That means to transmit one bit of data from one end to another end, what's the total energy consumption required to transmit? Okay, so typically for conventional DFB laser or edge emitting laser I mentioned, or VCSEL, is about hundreds or thousands of femtojoule per bit kind of energy efficiency. With photonic crystal, in fact, in Japan, there are a few groups can, by shrinking the cavity size, demonstrate in the energy efficiency in the order of femtojoule per bit range. Okay, very powerful. The record is 1 femtojoule per bit. So we are looking to, can we do something similar on silicon with photonic crystal to achieve femtojoule per bit or even less energy efficiency? And we have an active project. One of the students just presented some simulation result here. Shows basically, of course, you need to scale the cavity. So simply by shrinking the laser cavity size, you can reduce the energy efficiency. Of course, there are many more things behind in terms of the cavity quality factor, confinement factor, etc. So we don't dig into very details here. The bottom line, we have to look into the cavity in the scaling. So that's what we work on, different kind of cavity. That's another cavity we work on called the barrier tunnel junction photonic crystal surface emitting laser. In this case, we have a gate media on the top here, hybridly integrated onto this single layer photonic crystal cavity. It's not a reflector now, so this cavity itself serves as a laser cavity. So it's different from the first one I discussed here. I don't have time to talk about this one now, but we demonstrated this cavity also recently. And even further, we reduce the thickness of the gate media by replace this 3-5 material with a single layer 2D material, like graphene type material, where we demonstrate the single sheet lasers on these materials. So, and then of course, we'll continue to work on some new things we can report later on once we publish later on. So in summary, in addition to the only demonstration of the lasers we have here, we also demonstrated the perfect absorption or some other material we proposed, metamaterials. We also looked into modulators for high-speed specialized modulator, could be applied for light applications. And we have a book published last year, summarized mostly our work and as well as some other groups. If you're interested, take a look on this one. So this is just the last slide before I summary. It's just what areas we work on. So I talked about this laser on chip on silicon for really work on energy efficient of data connectivity. We also look into UV lasers as well from DARPA. Like one of the application now we can see like COVID-19, right? With the UV disinfection to kill a virus, and as well as the sensing or application. We have another project on high power lasers where, okay, use the photonic crystal cavity structure. That could be very powerful, for example, for light applications. Okay, which we work on. Finally, we are looking for applications on integrated photonics, such as flexible biophotonics. I mentioned earlier, we can do flexible photonics. We can do multi-layer stacking for sensors. We have some patent on this as well with Professor Sang. And we have some recent work with Professor John Rogers from Northwest on bioimplantable, biodissolvable implant based on this membrane process. So here's the final slide, takeaway messages. So I argued laser and photonic technology are essential part of the data infrastructure for 5G, for IoT, for AI, big data. Silicon photonics is a solution to electronic scaling and the data explosion challenge. Laser remains to be one of the ground challenges in silicon photonics. Scaling of on-chip lasers based on photonic crystal cavity microtransfer printing is one of the most promising approaches towards energy efficiency, photonic and electronic integration. Finally, I believe the future of light of photonics is bright. And indeed, everybody now argue the age of light is now, sense. And of course, we're always looking forward for highly motivated students interested to work on these exciting areas of photonics. And thank you for your attention.
Thank you, Dr. Zhou. We will now open it up for questions from anybody that has any. As I said earlier, please go ahead and post any questions you might have in the Q&A box on the right, top right hand of your screen. I'm actually going to pull something from your very last thing that you said. You said students are welcome to come work with you in your lab, and I saw undergrad in there. This seems like a very difficult, very complex area of study. How should undergrads go about coming to you to start working and start learning about photonics?
Oh, good point. Thanks, Jeremy. Yeah. So yeah, sometimes students feel, oh, this could be something physical, something math, or too complicated. In fact, no. There are so many simple things undergrad can get in. In fact, I have been multiple undergrad working in my lab. We have now currently we have one undergrad worked for me for 2 years now in my lab. Really, you can start with something very simple to just do some kind of simple testing on those devices, and then of course you can involve in some simple designs. And then many times, you don't need a kind of deep understanding to be able to get a simple grasp. For example, we talk about this structure modeling, other things. Those things can be done by simply optical design. There are software package available, and we typically have students work with kind of graduate students side by side, so they kind of learn. As long as you have some simple basic understanding knowledge of electroengineering or physics, you are ready to do things we can do in our lab. So yes, welcome any level of students working in my lab. I even had in fact high school student working in my lab as well for summer.
Fantastic. So I know that you're not the only one working on photonics in the electrical engineering department. I know there are other people there. I also know that you're in the process of starting a photonics center. Is that something you're able to talk about a little bit?
Right. Yeah. Good point. Okay. So indeed, let's see. I didn't have time. Okay. Here's actually my hiding slide. Thank you. So indeed, photonics is one of the strengths, I guess, at the UTA. We have lots of excellent professors, faculty groups working at the photonics area. So I just highlighted a few of them in the sense of working in the area of photonics. In addition to myself, I mentioned work on silicon photonics or devices, optoelectronics, lasers. We have Professor Vassiliev work on communication, nonlinear optics, quantum optics. We have Professor Magnussen, is very well known on the guided motor resonance principles and all the devices related on these areas for imaging for sensing. We have Professor Sang, is expert on optofluidics, ring resonators, on bio-based, liquid-based lasers, and lots of nice work there in her group. We have a joint project on optofluidic-based sensors as well, and we have other group like Professor Chen from physics on energy, for sustainable society. And in fact, this image is a little bit old. You can see already we have almost 100 people of UTA alone. Okay, at one of the first symposium, I guess Robert and a few other organized on this photonic symposium. And the last few years, we have additional faculty members like Professor Professor Jim Coleman is a National Academy of Engineers. Professor Katrina Coleman is also fellows at IEEE USA, all very well known, as well as Professor Diana Hafeko just joined us this fall as a double department chair. Is one of the world-renowned photonics expert in the areas. So you can see we have a big presence. Many faculties work on either core photonics, applied photonics to their research. So I see there lots of faculty groups at the UT, and that's why we try to build a center to attract more people in terms of research, also to provide a venue for workforce development. There are huge kind of demand for photonics based or optics based kind of people at all levels to be able to support this photonic era in this coming century. And finally, of course, many of us use this kind of clean room, part of the UTA Nanotechnology Research Center, clean room, very world-class facility to do all the research. That's what I'm using on. That's my lab located above this clean room facility. So we have an excellent facility and lots of excellent faculty at the UTA. Thank you.
Thank you. So again, for anybody that's attending that might have a question, go ahead and type that in the Q&A box. Since I don't see one right now, I have another question for you, sir. What are some of the applications? Like you've talked about the research and the things that you're developing and that have been developed throughout the last couple decades or whatever. What are some of the applications that we could see what you're working on out in the world?
Right. So there are different level of application or different pieces. In fact, let's say maybe I go back to my slides. I can highlight a few things. Again, the talk here is very high level. I didn't intend to provide too much detailed discussions on its specific things. But again, for this laser, for example, we're working on now, we have a few patents. We had some SPR, STTR project try to pursue. Of course, the challenge here is the performance and the cost always be the issue. If you want to, for example, I mentioned a VCSEL. If we want to compete with VCSEL, VCSEL now is cost about $1 or so, commercially. So it's can be very cheap. But the current VCSEL is hard to integrate on silicon chip. It's also does not scale with different wavelengths. So we believe our technology can be built on chip, can also scale to long wavelengths. That's one of the areas where we are looking at as well, where the traditional laser may not perform well, and this kind of technology can be applied for applications in longer wavelengths for sensing, for on-chip integration. Another area actually we kind of looking at is kind of another laser as well for high power lasers, which we work on. In fact, we submit a proposal as well, looking for develop a technology for light applications. We have another one called high spatial light modulators, which can address the issue of LiDAR beam scanning. Okay, that's kind of a few things kind of my core interest. And in addition, on the sensor area, that's so broad, right? We know Professor Mechanism has a company on this resonant sensors and the structures, I guess, have some success there. We are interested as well on some kind of gas chromatography for gas separation with Professor Sang on some project. Some of the things we're working on with Professor John Rogers on brain implantable sensor could be very impactful for put an optical sensor in the brain. You guys saw the news from Elon Musk talk about the kind of implant of electronic sensors in the mouse. You can see it's kind of big news probably a few weeks ago. But there are issues with electrode where you have this kind of compatibility, infection concerns. So optics could have an advantage there, of course, but there are some challenges as well. So some of the things we are doing here can potentially also be able to used for brain monitoring, for brain control, for brain function control, or even to cure the disease in the brain, and of course, and for wearable other sensors as well. So the potential applications are humongous. I mean, hardly can say something which optics cannot penetrate. Of course, there always come back to, of course, the performance cost issue. But otherwise, photonics, I think long term will work along with electronics and other technology, have lots of potentials not potentials, real applications for consumer electronics and data applications.
Fantastic. Well, I don't see any other questions at the moment, so I'm going to go ahead and wrap it up. Thank you so much, Dr. Zhou, for being here today and for explaining about the types of research you're doing on a very high level, and making it mostly understandable for those of us that aren't experts at photonics. I'd like to point out to those attendees that are still here, or that are here, not still here, that we do offer virtual brown bag events every day during the week. On Fridays, we have a faculty, industry, or alumni presentation about the kind of applied research and research out in the world. Next Friday at noon, it'll be Ernest Huffman, who's the program manager for aviation planning and education for the North Central Texas Council on Governments. And he's going to talk about integration of autonomous drone technology into the DFW Metroplex. So you can find the link to our entire schedule on our website. The link is in the chat, or sorry, the Q&A box over here on the right-hand side. And again, thank you to Dr. Zhou, and thanks everybody for attending today, and have a great weekend.
Thank you.